Hello, everybody. First of all, I would like to thank organizers for inviting me. It's a great honor to give a talk here at CCP4 SW2020 in front of all of you. My talk is devoted to local and global analysis of macromolecular B values. And I'm going to discuss the local analysis and global analysis, and as well as their application. Under global analysis, we mean overall statistical model of B-value distribution, and in local analysis, we implement the inspection of potential lighter and heavier atoms. B-values reflect the combined information about uncertainties of atoms, their mobility, as well as the resolution and noise in the experimental scattering data. One of the problems with absolute B-value is that if one adds or removes the constant B-value to or from all atoms, the average B-value will change accordingly. By sharpening or blurring the data before refinement, one can increase or decrease the average arbitrarily. If there are no negative B-values as a result of such operation, it will only affect the scale between observed versus calculated Fourier coefficients, as well as causing the resultant map to be blurred or sharpened. I should note here that shifting all B-values change the average, but does not change the variance. So, therefore, the distribution of B-values is a better indicator of model and data quality than the average B-value. So, our main approach that statistical analysis of B-value distribution, as well as their differences of B-values for neighboring atoms, can shed light into the validity of atomic models and even may show the locations of misinterpretation of the experimental data. Since B-values are proportional to the variances of positional parameters, we expect that the distribution of B-value will obey the distribution of variances. In Bayesian statistics, it's common to use inverse gamma distribution as a conjugate prior of normal distribution, a conjugate prior of the variance of normal distribution. So this is why we expect that the distribution of B-values may be modeled as a shifted inverse gamma distribution. Inverse gamma distribution is a univariate continuous distribution with shade parameter alpha, scale parameter beta, and for shifted inverse gamma distribution, we add the additional shift parameter B0, additional shift parameter B0. We add shifts to inverse gamma distribution to account possible mishandlings by under or over blurring. The initial value of the shift parameter may be equal to the minimum B value, and we estimated the parameters of inverse gamma distribution by method of moments and refined the shifted inverse gamma distribution parameters using maximum likelihood estimation with Fisher scoring method. Since three-dimensional maps used for model building in crystallographic and cryo-EM experiments correspond to the densities of electrons and electrostatic potentials, it is interesting to analyze the effect of B-values on peak heights as the center of atoms within a given resolution. Here you can see that the resolution depends on B-values as well as the resolution. You can observe that as resolution rises, the distribution becomes more narrow. Hence, at a higher resolution, the little differences in B-values have much more dramatic effect on density level than the lower resolution. We downloaded all structures from the PDB by the last of November. You solve it by X-ray crystallography within the resolution 1.5 angstroms, 1.5 and 3 angstroms, and plotted the alpha and beta parameters. If alpha and beta parameter of the model of interest is the outside of this region defined in the plot, these structures should be considered for a refinement with careful consideration of atoms types as well as erroneous loops. This plot was derived from more than 90,000 of PDB structures in total. There are many structures with a high alpha and beta parameters, which are unfortunately very difficult to classify. In this particular example, you can see that the alpha and beta parameters are far outside of the so-called allowed area. The deeper analysis of density map showed that the most of methionine side chains are missing the structure, and there are some heavier atoms interpreted as water molecules. Crystallization condition indicates that there was calcium, no, in this structure there was a chlorine, sodium, potassium, phosphate, as well as thiamine diphosphate molecule present. And further analysis of the map showed that these molecules and ions are present in the crystal. After a few rounds of the model building and rebuilding, values of R and R3 decreased. Sometimes B-value distribution may exhibit multimodality for some structures. There are second possible reasons for this. The first, it may be the natural property of molecules within their environment, where the different components have different number of neighbors to interact with, and in such cases, the different subunits and domains may have different levels of mobility. And this reflects in B-value distribution. We expect that each individual structural unit will exhibit the shifted inverse gamma distribution behavior with different parameters. And the second reason, there's some parts of the structure may be placed wrongly, and essentially this means that there is very weak or no evidence to support the presence of this part in the structure, those parts should be considered with extreme care. Here's an example of the structure with three chains, A, B, and C. A and B chains are identical, and as you can see from the table, they have many contacts, non-covalent interactions between them, and C chain is more independent, and the part of the B-value distribution which form the second mode is corresponds to the atomic B-values of C chain, and you also can see that the electron density is weaker here. In this example, the higher B-values and more smeared data is a result of the incorrectly placed domain. And this the part in this distribution which forms the second mode, with higher B-values, correspond to this disordered domain in the structure. So how we deal with multimodal p-value distributions? We analyze multimodal distributions using the mixture of shifted inverse gamma distributions. We estimate parameters of shifted inverse gamma distribution mixture in two steps. First, we estimate the Gaussian mixture parameters to model the peak height distribution, and using the Gaussian mixture parameters as initial values, we estimate shifted inverse gamma parameters, the parameters of shifted inverse gamma distribution mixture using B values. This example is given for the structure 1AON, and at least for this particular example, you can see that this clusterization works sufficiently well. And here's the parameters of the shifted inverse gamma distribution mixture and its parameters. Now local analysis. As we know, the ADPs of atoms should be similar to their surrounding atoms' ADPs. When neighboring atoms have very different B values, there may be two reasons. First reason is atoms may be wrongly placed, and second, atoms may be wrongly parameterized. For example, occupancy and element types may be wrong. We are designing algorithms to accurate analysis of B values for neighbors based on their relative peak heights and some statistical techniques. Firstly, we define all neighbors for each atom. Here we use the, for each atom within a defined distance. Here we use the efficient cell algorithm, which was implemented in GIM library. Then we compare the B value of atom with the first and third quartiles of its neighbors' B values. And here we pose the question as follows: how we should change the occupancy so as atoms' B value will be equal to the B value, neighboring B value. And we analyzed it up to 2,000 entries from the PDB with 2 angstroms and higher, resolution of 2 angstroms and higher, and found more than 600 of entries containing potentially heavier atoms. Our algorithm marks potentially heavier and lighter atoms with optimal occupancy calculated regarding to the surrounding of each atom. In local analysis, we carefully consider potentially heavier atoms. Heavier atoms may occur as a result of wrong parameterization, as I said. I mentioned about the structure where thiamine diphosphate molecule was modeled as 10 molecules of water. In this example, you can see that here the heavier atom with 6 coordinated oxygen with which was modeled as a water, which might be magnesium. According to crystallization condition, the crystallization condition indicates that there was added magnesium chloride. There are many structures with metal links, but our algorithm does not highlight them because they are modeled correctly. Among structures we analyzed, there was a case where when the calcium atom was detected as a heavier atom with optimal relative occupancy 1.38, and we expect that the crystallization condition indicates that there was added cadmium sulfide, and we expect that its cadmium in half occupancy with water modeled as calcium, and After rebuilding, we can see the map again. I don't know if there is a functional importance or not, but according to the difference map here, sorry, I can't find this dot. According to the difference map here, we can see that this according to the difference map, we know that this this atom and also its surrounding should be considered for rebuilding and refinement, especially if they're in case that it has some functional importance. And I was missing the slide in this here. Sorry. As we know, the calcium has 20 electrons and cadmium has 48, and with the optimal occupancy 1.838, we can expect that there should be approximately 28 electrons, and with half occupancy with water, cadmium, 24 plus 4, it gives us 28 electrons, which also gives us notion that here should be in this position cadmium with a half occupancy with water. All methods mentioned above was implemented as parts of our Python program named to be valid, which will be available online soon. I would like to thank my conclusions, and sorry. As I said, there is a need for model and as well as validate the atom displacement parameters. And shifted inverse gamma distribution may be used to model the inverse gamma distribution. If the B-value distribution overall whole structure does not obey the shifted inverse gamma distribution, the separated chains and domains will behave like shifted inverse gamma distribution. B-values differences for neighboring atoms can show the locations of misinterpretation of the experimental data. So acknowledgements, I would like to thank my group, Computational Structural Biology group in Baku, my group mates Kaveh Babai, Humay, and Leila. Also, I would like to thank Computational Structural Biology group and MRC LMB Cambridge. Part of my work has been done during my visit Garib's group in Cambridge. So thank you for your attention.
Thank you, Rafiga. Do we have any questions on Rafiga's talk? I guess Randy first, and then Paul, Kevin down there.
I actually have two questions. One of them is, you talked about the B0 value and how that might indicate mishandling of the data in merging and scaling. But could it also arise because you've got a mixture of a structure where the internal content of a unit cell has one distribution, but then you have lattice disorder superimposed?
Yes. In case of multimodality, of course, the distribution of the second mixture, the second part of the mixture is shifted right, and the parameters are higher, as of course, but this is the it's most mirrored that data, and it has more errors than the other structures and then the first part, for example. And
so the second question is, what you're doing is refinement, and then you take the B factors from the refined model and you do refinement, and then you take the B factors from the refined model and work out the distribution. Do you have a way of taking the intensity distribution as a function of resolution and predicting what would be the parameters of this shifted inverse gamma distribution that you'd expect in your model?
If I take the low resolution, or?
No, just take the intensity distribution, so the intensity as a function of resolution.
never had, but it may be one thing to be done. Thank you. And for the regarding to the first question, it's natural property actually for the second part of the mixture to be shifted.
That was a very nice talk. I was wondering roughly how many atoms...
I can see the...
Hello.
Hey.
So I was wondering how many atoms do you need to estimate alpha and beta, and would that allow you to do a moving average estimation of alpha and beta along a chain?
Good question, thank you. As it's a statistical method, of course, we need the sufficient amount of data. Currently, we look to structures with more than 500 atoms. It's what has done, but yes. When the data is not amount, it fits to Morse gamma distribution, but as you can understand that the distribution will not be very well looking.
Do structures refined with Buster show the same distribution? And if they
Sorry,
do,
Paul, yes, please.
Hello.
Sorry.
Do structures refined with Buster show the same distribution? And if the answer is yes, do you foresee this as a validation tool to be used by the WWPDB?
Thank you for the question. Excellent question, as by you as always. Yes, we hope that it will be used as one of the validation tools, because the inverse gamma distribution parameters for the most structures gave us some plot where we have some allowed area, which and on the other hand, our tool gives the range of outliers, which is the range of atoms which should be considered for the refinement. And also, in local analysis, we highlight atoms that may be modeled wrongly. And I should note here that when we published the first paper, the amount of structures from which we derived the alpha beta plot was twice less. Now it's more than 900, but the plot is the same, which shows that this is more or less constant.
Okay, thank you. I don't see any more questions. Okay, maybe just one more then, because it's time to move soon to lunchtime, bites and lunch. So this will be the last question.
Yeah, very nice talk, very nice study.
Thank you. Hi. Thank you. Yes.
On one AON, I've just had a look at the data, and they are quite anisotropic, and they've been quite brutally truncated at at the local I over sigma of over 6 in one direction. So how did you refine that structure? Was the anisotropy modeled in the refinement? And in any case, there is a direction in which there would be missing data that was still strong. So your relationship between peak heights and B factors would be messed up in that case. We can have a look at it privately if you want.
No, question was pretty long. It's a structure with, if I'm right, with the resolution 2.9, and I should note that all structures we analyzed, firstly, were refinement by RIFMAC to handle some moments with different refinement programs, to get our data to be more objective, and with using the same program. But this is not the exception. We use the We use the default refinement mode for RefMark, and if you are asking about the restraints, then the unrestrained refinement, this works pretty same. But maybe I didn't understand the question correctly.
This data set is problematic. It's got strong anisotropy. That means significant data have been truncated in one direction, but even internally, the local averages of I over sigma look quite tormented. So this is not a particularly representative data set.
This is just one example. We had up to 9% of structures to behave to exhibit multimodal B-value distribution, and this one of those examples. The other example with clear B-model distribution, for example, 1MOW. There are plenty of data which I can provide you, but this is one of the examples, maybe not the best one.
Okay, I think we have to stop here in the interest of lunch. Please, I'd like to conclude the session by thanking all the speakers again.